Sri Jayendra Saraswati Vidyalaya Matriculation High Secondary School, Singanallur.
Namaste. Today we are going to see the problems in Class 12 Physics Lesson 8 Dual Nature of Radiation. First problem is, how many photons per second emanate from a 50 megawatt laser of 640 nanometer? So 640 nanometer is the wavelength of the laser. 50 megawatt is the power of the laser. So first we will write the given data. Power is 50 megawatt. The wavelength is 640 nanometer. We know the H value, which is Planck's constant, which is 6.6 into 10 power minus 34 joule second. The value of C, that is the velocity of light, is 3 into 10 power 8 meter per second. So we are supposed to find the number of photons. So number of photons which emanate per second is NP, is given by power divided by the energy. So power divided by energy is E is equal to H nu. Nu is equal to C by lambda. Hence E is equal to Hc by lambda. So when you substitute in the equation of number of photons, we get Np is equal to P lambda by Hc. Now substitute the given data of power, lambda, H and C, we will get the answer. So substituting the values, we get 50 into 10 power 3 into 640 into 10 power minus 9 divided by 6.6 into 10 power minus 3 into 10 power 8. So multiplying and cancelling, we get the answer as number of photons is equal to 1.61 into 10 power 17. So these many number of photons emanate from 50 megawatt laser whose wavelength is given by 640 nanometer. The second problem is, calculate the maximum kinetic energy and maximum velocity of photoelectrons emitted when the stopping potential is 81 volt for the photoelectric emission experiment. So here the stopping potential V0 is given as 81 volt. We know the charge of the electron is 1.6 into 10 power minus 19 coulomb, and mass of the electron also we know as 9.1 into 10 power minus 31 kilogram. We are supposed to find the maximum kinetic energy and maximum velocity. So first let us find the maximum kinetic energy. Kmax, which is the maximum kinetic energy, is given by E into V0, where E is the charge of the electron, V0 is the potential, stopping potential, whose values are given in the data. So Kmax is equal to E into V0, which is equal to 1.6 into 10 power minus 19 into 81, which is equal to 129.6 into 10 power minus 19, which can also be written as 1.29 into 10 power minus 17 joule. Hence, the maximum kinetic energy is 1.3 into 10 power minus 17 joule. Next, we have to find the maximum velocity of photoelectron. The expression for maximum velocity is given by Vmax is equal to square root of 2 into E into V0 divided by M, where E is the charge of the electron, V0 is the stopping potential, M is the mass of the electron. So substituting these values, we get square root of 2 into 1.6 into 10 power minus 19 into 81, the whole divided by 9.1 into 10 power minus 31. So cancelling this, multiplying the numerators, Dividing by the denominator, finally we get the answer as Vmax is equal to 5.3 into 10 power 6 meter per second. This is the maximum velocity. Now the third problem. Calculate the energies of photons associated with the following radiation. First one, violet light of wavelength 430 nanometer. Second one, X-rays of wavelength 0.1 nanometer. The third one is radio waves of 1 meter. So we are supposed to find the energies associated with each wavelength. So we will start with the given data. H is equal to Planck's constant, which is equal to 6.6 into 10 power minus 34 joules second. C, velocity of light is 3 into 10 power 8 meter per second. Energy of photon E is given by E is equal to H nu. Mu is equal to C by lambda. Hence E is equal to Hc by lambda. First we will find the photon energy of the photon associated with violet light. So for violet light, the lambda is given as 430 nanometer. Hence E is equal to Hc by lambda. Substituting the data, we get 6.6 into 10 power minus 34 into 3 into 10 power 8, the whole divided by 413 into 10 power minus 9. Simplifying, we will get 4.794 into 10 power minus 19 joule. Here the energy is in the unit of joule. We need to convert this unit of joule into electron volt. Hence we divide the answer by 1.6 into 10 power minus 19. When we divide, you have converted joule into electron volt. Hence E is equal to 4.794 into 10 power minus 19 divided by 1.6 into 10 power minus 19 electron volt. So the answer is E is equal to 3 electron volt. This is the energy associated with violet light. Next we will find the energy associated with X-rays of wavelength 0.1 nanometer. Using the same formula, E is equal to H mu, where mu is equal to C by lambda. We substitute in that the given data, we get E is equal to 6.6 into 10 power minus 34 into 3 into 10 power 8, the whole divided by 0.1 into 10 power minus 9. Simplifying, we will get the answer as 198 into 10 power minus 17 joule. Here, once again, we have to convert this into electron volt. So once again, we divide it by 1.6 into 10 power minus 19. Hence, the energy associated with the X-ray is given by 12,375 electron volt. Next, the energy associated with radio waves. The radio waves wavelength is given as 10 meter. Once again, we substitute in the formula E is equal to H mu by lambda. We get E is equal to 6.6 into 10 power minus 34 into 3 into 10 power 8 divided by 10. We get the answer as 1.98 into 10 power minus 26 joule. Once again, we are supposed to convert this unit of joule into electron volt. Hence, we divide once again this value by 1.6 into 10 power minus 19 to convert it into electron volt. Hence, the answer is the energy associated with radio waves is equal to 1.24 into 10 power minus 7 electron volt. Hence, we found the energies of the photons associated with violet ray, X-ray and radio wave. Fourth problem, a 150 watt lamp emits light of mean wavelength of 5500 Armstrong. If the efficiency is 12%, find out the number of photons emitted by the lamp in 1 second. So the given data is the power is equal to 150 watt. The wavelength is 5500 Armstrong Planck's constant value we know as 6.6 into 10 power minus 34 joule second. The velocity of light capital C is equal to 3 into 10 power 8 meter per second. We are supposed to find the number of photons emitted. The number of photons emitted per second is given by n is equal to p lambda divided by hc. Here the efficiency is given as 12%. So eta, which is the symbol of efficiency, is given by eta is equal to 12 by 100, which is equal to 0.12. Now this efficiency also we are supposed to include in the number of photons. Hence the equation for number of photons emitted per second is given by n is equal to p eta lambda by hc. Now substitute all the values from the given. We get 150 into 0.12 into 5500 into 10 power minus 10 the whole divided by 6.6 into 10 power minus 34 into 3 into 10 power 8. So simplifying this you get the number of photons as 5 into 10 power 19. Now the fifth problem. How many photons of frequency 10 power 14 Hz will make up 19.86 joule of energy? Here the energy is given, the frequency is given, we are supposed to find the number of photons. So we will start our problem with the expression for total energy. Total energy emitted per second is given by power into time. Here, the energy value is given in terms of joule, which is 19.86 joule. So this energy is equal to power into time. So time is, the unit is second. So the second when you take to the equation other side, it comes to the denominator. Hence the value becomes 19.86 into joule divided by second. Joule by second or joule per second is called as watt. Hence the power is 19.86 watt. Now we will find the number of photons. Number of photons n is equal to p divided by h nu, where p is Planck's constant, h is Planck's constant, mu is the frequency, p is the power. So substitute the given data, you get the answer as 19.86 divided by 6.6 into 10 power minus 34 into 10 power 14, which is finally equal to 3 into 10 power 20. Hence the number of photons emitted is 3 into 10 power 20. Sixth problem. What should be the velocity of the electron so that its momentum is equals that of 4000 Armstrong wavelength photon? We are supposed to find the velocity of electron. We know the formula for de Broglie wavelength of electron is lambda is equal to h by p, where p is equal to mv. So when you substitute mv instead of p, you get v is equal to h by m lambda. Now substitute the given value, we get 6.6 into 10 power minus 34 the whole divided by 9.11 into 10 power minus 31, which is the mass of the electron, into wavelength value is 4000 into 10 power minus 10. Now simplifying you get the velocity as 1811 meter per second. Seventh problem. When a light of frequency 9 into 10 power 14 Hz is incident on a metal surface, photoelectrons are emitted with the maximum speed of 8 into 10 power 5 meter per second. Determine the threshold frequency of the surface. So the frequency of the light is given, the speed of the light is given. We are supposed to find the threshold frequency, which is the minimum frequency for the photoelectrons to be emitted. Hence, we use the Einstein's photoelectric equation, which is half mv squared is equal to h into mu minus mu naught. We are supposed to find the threshold frequency, which is mu naught. So mu naught alone we have it in LHS. All the remaining terms we take it to the RHS. So we get h mu naught is equal to half mv squared minus h mu. We want to find only mu naught. So once again we divide this equation, the RHS, by h. So we get the expression as mu minus mv squared divided by 2h. Now substitute the values of mu, velocity, Planck's constant. We get the answer as 9 into 10 power 14 minus 9.11 into 10 power minus 31 into 8 into 10 power 5 the whole square divided by 2 into 6.6 into 10 power minus 34. Simplifying, we get the threshold frequency as mu naught is equal to 4.6 into 10 power 14 Hertz. Eighth problem. When a 6000 Armstrong light falls on the cathode of a photocell, photoemission takes place. If a potential of 0.8 volt is required to stop the emission of an electron, then determine first one, frequency of the light, second one, energy of the incident photon, third one, work function of cathode material, fourth one, threshold frequency, fifth one, the net energy of the electron after it leaves the surface. So first we will start with the given data. Wavelength is given as lambda is equal to 6000 Armstrong, which is equal to 6000 into 10 power minus 10 meter. The stopping potential V0 is given as 0.8 volt. First we will find the frequency. Frequency mu is equal to C by lambda. C value you know, lambda value is given in the data. Substituting, we get 3 into 10 power 8 divided by 600 into 10 power minus 10. Simplifying, we get the frequency of the light as 5 into 10 power 14 Hertz. Second one, we have to find the energy of the incident photon. E is equal to h nu, which is equal to 6.6 into 10 power minus 34, which is the h value, which is the Planck's constant, into mu. Before, in the first one, we found the frequency. That value I am substituting here. So 6.6 into 10 power minus 34 into 5 into 10 power 14, which is equal to 33 into 10 power minus 20 joule. Once again, here the unit of energy is in joule. We are supposed to convert it into electron volt. So we divide this answer by 1.6 into 10 power minus 19. Hence the answer is 20.625 into 10 power minus 1, which is equal to 2 electron volt. So the energy of the incident photon is equal to 2.06 electron volt. Next, we have to find the work function of the cathode material. The expression for work function, which is W0, is equal to h mu minus E V0. H value we know, mu value also we have found, E value we know, stopping potential also we know. So substituting these values, we get the answer as 6.6 into 10 power minus 34 into 5 into 10 power 14 minus 1.6 into 10 power minus 19 into 0.8. Here once again, the answer is in joules. We have to convert it into electron volt. So once again, we divide it by 1.6 into 10 power minus 19. So the answer is W0 is equal to, which is the work function, which is equal to 1.26 electron volt. Fourth one, we are supposed to find the threshold frequency. Threshold frequency mu naught. We know that W naught is equal to h mu naught. So mu naught will be equal to W naught divided by h. W naught, before only we have found out it as 1.26. So 1.26 the whole divided by h value, which is the Planck's constant, is 6.6 into 10 power minus 34. Once again here we are converting into electron volt. Hence you multiply by 1.6 into 10 power minus 19. So the final answer is threshold frequency is equal to 3.05 into 10 power 14 Hertz. The last one, we have to find the net energy of the electron after it leaves the surface. So the energy E is equal to mu minus mu naught, where mu is the frequency and mu naught is the threshold frequency, which we had found previously. So substituting those values, we get 6.6 into 10 power minus 34 into 5 into 10 power 14 minus 3.06 into 10 power 14. Where 6.6 into 10 power minus 34 is the Planck's constant. E is equal to h mu. The h they have taken outside the bracket. So E is equal to 6.6 into 10 power minus 34 into 1.94 into 10 power 14. Simplifying, we get the answer as E is equal to 0.8 electron volt. Here also we have to convert this joule into electron volt. So once again dividing by 1.6 into 10 power minus 19. Finally, we get the net energy of the electron after it leaves the surface is equal to 0.8 electron volt. The ninth one, a 3310 Armstrong photon liberates an electron from a material with energy 3 into 10 power minus 19 joule, while another 5000 Armstrong photon ejects an electron with energy 0.972 into 10 power 18 joule from the same material. Find the value of Planck's constant and threshold wavelength of the material. Here two data is given. First data is from 3310 Armstrong photon, an electron is emitted whose energy is 3 into 10 power minus 19 joule. So here the energy of the ejected electron is given by E is equal to hc by lambda minus hc by lambda naught. Using the first data, we substitute the values, we get 3 into 10 power minus 19 is equal to hc, we can take it common from the RHS, hence we get hc bracket 1 by lambda minus 1 by lambda naught. Substituting the lambda value, lambda naught we do not know, that only we are supposed to find. Lambda naught is the threshold wavelength. Hence, we get the equation as 3 into 10 power minus 19 is equal to hc into 1 by 3310 into 10 power minus 10 minus 1 by lambda naught. This equation you keep it as 1. Now see the second data. In the second data, the energy is given as 9.72 into 10 power minus 20 and the lambda value is given as 5000 Armstrong. So using this, we write the energy equation as E is equal to hc by lambda minus hc by lambda naught. Once again hc you can take it common, hence E is equal to hc into 1 by lambda minus 1 by lambda naught. Substituting the lambda value, we get 9.72 into 10 power minus 20 is equal to hc into 1 by 5000 into 10 power minus 10 minus 1 by lambda naught. This equation you keep it as 2. Now we have to subtract equation 2 from 1. So when you subtract, we get 3 minus 0.972. The 10 power minus 19 we have taken outside the bracket. Hence you get 3 minus 0.972 into 10 power minus 19 is equal to, in the RHS also we take the common terms outside, which is hc divided by 10 power minus 10. So inside the bracket we will have 1 divided by 3310 minus 1 divided by 5000. So we have to cross multiply, hence we get 2.028 into 10 power minus 19 is equal to h into 3 into 10 power 8 divided by 10 power minus 10 into, when you do the cross multiplication, we get 1690 divided by 3310 into 5000. Hence, H value is equal to 2.028 into 10 power minus 19 into 10 power minus 10 into 3310 into 5000 divided by 3 into 10 power 8 into 1690. So, simplifying this, we get the H value as 6.62 into 10 power minus 34 joule second. Now, the threshold wavelength is given by lambda naught is equal to hc by w naught. So first we will find the w naught. After that we will substitute in this equation to find the threshold wavelength. So w naught, we know the expression for w naught as w naught is equal to hc by lambda minus e. So substituting the values, we get the value of w naught as 3 into 10 power minus 19 joule. Hence, substitute this value in the expression for threshold wavelength. We get lambda naught is equal to 6.62 into 10 power minus 34 into 3 into 10 power 8 divided by 3 into 10 power 10 power minus 19, which is equal to 6620 into 10 power minus 10 meter, which is the final threshold wavelength. Tenth problem. At the given point of time, the energy received by the earth from sun at 4 calories per centimeter square per minute. Determine the number of photons received on the surface of the earth per centimeter square per minute. The value given is mean wavelength of the sun is 5500 Armstrong. So the energy value given is E is equal to 4 calorie. We have to convert it into joule. So the conversion is 1 calorie is equal to 4.184 joule. So here once again to convert this calorie into joule, we have to multiply by 4.184. And the lambda value is given as 5500 Armstrong. The number of photons received on the earth is N. We know that E is equal to h nu. Since the number of electrons is included, hence the equation becomes E is equal to N into h nu. We have to find the N value. So we reverse the formula. N is equal to h lambda by hc. Substituting the given data, we get the answer as N is equal to 4.65 into 10 power 19, which is the number of photons. Now the 11th problem. UV light of wavelength 1800 Armstrong is incident on a lithium surface whose threshold frequency is 4965 Armstrong. Determine the maximum energy of the electron emitted. So the given data is lambda is equal to 1800 into 10 power minus 10 meter. Lambda naught, the threshold wavelength is 4965 into 10 power minus 10 meter. H value, which is the Planck's constant, which is 6.6 into 10 power minus 34 joule second. The value of C, the speed of light, is 3 into 10 power 8 meter per second. We are supposed to find the maximum kinetic energy. Maximum kinetic energy, which is K max, is given by hc into 1 by lambda minus 1 by lambda naught, where lambda naught is the threshold wavelength. So substituting the given values in this formula and simplifying, we get K max as 4.40 electron volt, which is the maximum kinetic energy. 12th problem. Calculate the Broglie wavelength of a proton whose kinetic energy is equal to 81.9 into 10 power minus 15 joule. The given data is mass of the proton is 1836 times that of the electron. So mass of the proton, we know that it is 1.67 into 10 power minus 27 kg. Kinetic energy is 81.9 into 10 power minus 15 joule. Hence, de Broglie wavelength is given by lambda is equal to h by square root of 2m into kinetic energy. Now, substitute the given data in this formula, we get de Broglie wavelength is equal to 6.6 into 10 power minus 34 the whole divided by square root of 2 into 1.67 into 10 power minus 27 into 81.9 into 10 power minus 50. Further simplification, we get the lambda value as 4 into 10 power minus 14 meter. Now the 13th problem. A deuteron and an alpha particle are accelerated with the same potential. Which one of the two has greater value of de Broglie wavelength associated and less kinetic energy? So, using the de Broglie wavelength formula, the deuteron and alpha particle are accelerated with the same potential. Hence, their velocities will be the same. So, we know the expression for lambda as lambda is equal to h by square root of 2m v0 q. Here, v0 is constant for deuteron and alpha. 2 is also a constant. So, we can write that lambda is proportional to 1 by square root of m into q. Hence, lambda of deuteron is proportional to 1 by square root of 2 m, that is mass of the deuteron, into charge of the deuteron, and lambda suffix alpha, that is wavelength of alpha particle, is proportional to 1 by square root of 8 into mass of alpha particle into charge of alpha particle, which is m suffix alpha and q suffix alpha. Now we have to divide lambda alpha divided by lambda deuteron. Hence we get lambda alpha by lambda deuteron is equal to square root of 2mq divided by 8mq. Hence we get square root of 2 by 8, which is equal to square root of 1 by 4, which answer is 1 by 2. Hence, lambda alpha divided by lambda deuteron is equal to 1 by 2. Hence, lambda deuteron is equal to 2 into lambda alpha. That is, the wavelength of deuteron is equal to twice the wavelength of the alpha particle. Next, we have to find the kinetic energy. So, for the same potential of acceleration, the kinetic energy is proportional to the charge. We know the charge of the deuteron is plus E, charge of the alpha particle is plus 2E. Hence, kinetic energy of deuteron is equal to kinetic energy of alpha divided by 2, because the kinetic energy is proportional to the charge. Hence, the charge of the alpha particle is more than that of the charge of the deuteron. An electron is accelerated through a potential difference of 81 volt. What is the de Broglie wavelength associated with it? To which part of the electromagnetic spectrum does this wavelength correspond? Hence, the de Broglie wavelength of electron is given by lambda is equal to h by square root of 2m eV. Hence, we know that lambda is equal to 1.23 into square root of V, where V is the potential. The remaining terms are constant, so it is not written. Now we know the formula for lambda is equal to 1.23 divided by square root of V. V value is given as 81. Hence, substituting this, we get lambda is equal to 1.36 Armstrong. This wavelength corresponds to the X-ray. Hence, X-ray is a part of electromagnetic spectrum, and this wavelength of 1.36 Armstrong corresponds to the X-rays. And X-ray has the wavelength ranging from 10 power 8 to 10 power minus 12 meter. The 15th problem. The ratio between the de Broglie wavelength associated with proton accelerated through a potential of 512 volt and that of the alpha particle accelerated through a potential of x volt is found to be 1. We are supposed to find the value of the potential with which the alpha particle is accelerated. We know the de Broglie wavelength formula as lambda is equal to h by square root of 2mq into v. Hence, lambda is proportional to h divided by square root of m into q into v. So the ratio of wavelength of proton and alpha particle is lambda p divided by lambda alpha is equal to square root of m alpha q alpha v alpha divided by m proton q proton and v proton. So separating this as mass, charge and potential, we get lambda p divided by lambda alpha is equal to square root of m alpha divided by mp into q alpha divided by qp into v alpha divided by vp. We know that m alpha by mp is equal to 4, q alpha by qp is equal to 2, v alpha divided by vp. V alpha value we do not know, so we keep it as x. Vp, that is the potential of the proton, we know it as 512, and lambda p by lambda alpha is given as 1. Hence, substituting in the above equation, we get 1 is equal to square root of 4 into 2 into x by 512. Simplifying this, we get 1 is equal to x by 64. Hence, x is equal to 64 volts. So the value of x, that is the potential with which an alpha particle is accelerated, is found to be 64 volt.